Hello students, now we shall look at one more problem. In a power plant, we use coal for burning, and we have to calculate the amount of air required to burn the coal so that we can have the suitable blowers. Now I will read the question. Air at 1 bar and 25 degrees centigrade is supplied to a furnace of a steam power plant which burns coal at a rate of 2,40,000 kgs per hour. If we need 14 kg of air for each kg of coal burned, what should be the volume flow rate of air in meter cube per hour? So this is a question, practical problem of a steam power plant which is using coal as a fuel, and it is burning 2,40,000 kgs of coal per hour, and for each kg of coal it requires 14 kg of air, and this air is supplied at 25 degrees centigrade and 1 bar pressure. Okay, so very simple it is. So volume flow rate of air is V, capital E. Please understand, capital V stands for the volume and small v stands for the specific volume, is meter cube per kg. Volume units are meter cube, whereas small v is specific volume, that is meter cube per kg. So you can see capital V, that is volume of air, is equal to mass of air into specific volume of air. Mass of air is in kg and specific volume is meter cube per kg. So this kg they cancel, and what will remain is meter cube on both left hand side as well as right hand side of the equation. Now what is given for every kg of coal? 14 kg of air is required. So mass of air divided by mass of coal is equal to 14 kg, right? That is given. That is, mass of air is equal to 14 into mass of coal. Therefore, now using these two relationship, volume of air, V, air, is equal to 14 into mass of coal into specific volume of air. So this relationship we will use in solving this problem. Okay, but now first we will find out the small v, that is specific volume of air at the furnace inlet. So again, using the ideal gas equation relation, PV is equal to RT here. So this when I am using small v, that is specific volume, M will not come here, okay, because M I have taken in the initial relationship only. So here specific volume of air is equal to RT by P, and now we will find out R. This is a gas constant for now air, and we have to find out the gas constant R from the universal gas constant, that is R bar divided by M. We will find out the R for the air, and the temperature is given at 25. So 25 plus 273 you will get in Kelvin, and P is given as 1 bar, so we will multiply it with 100. So the R bar is 8.3143 divided by air. Air is 28.97. The molecular weight of air is 28.97. If you can't remember this 28.9.7, I can give one more simple way. See, what is air? Air we consider as 80% nitrogen and 20% oxygen, right? That you know, air is 80% nitrogen and 20% oxygen. So what you will do? 80% means 0.8 into nitrogen is N2, that is 28. 0.8 into 28 bracket close, plus 20% is 0.2 into 32. Oxygen is 32. So if you simplify this, you will get as 28.97. Okay. So R is equal to 8.3, that is R bar, that is 8.3143 divided by molecular weight M is for air is 28.97 into T is 273 plus 25 divided by P is 1 bar, that is 1 into 100. So you get the specific volume V of air is 0.855 meter cube per kg. Okay. Therefore, the volume of air required is, now it is given volume of air required is 14 into 2,40,000 kg, that is coal is burnt, and per kg you require 14 kg of air into the specific volume, that is 0.855. So by solving this, you will get this volume of air required is 2.873 into 10 raised to 6 meter cube per hour. So this is the amount of air required, volume of air required per hour for the steam power plant to burn 2,40,000 kg of coal, for means that is consuming 14 kg of air per kg of coal burnt. So please understand this specific volume we have calculated. Then this specific volume we have calculated using the ideal gas equation, that is PV is equal to RT, and we have found out R of the air here by using molecular weight of R to be 28.97 and P was 1 bar, so we have multiplied by 100. So this is how you solve the numerical. This is a very practical numerical. I hope you please practice this, because this is a very interesting numerical, what I feel. In real life, when you work as engineers, you will be able to calculate this, because this has a very important bearing on the loss of energy also. If you are supplying more air, that is also waste, because the heat is carried away by the excess air. So please solve this numerical, and then we will see one more problem on ideal gas. Thank you.